this lecture is also different than all the lectures that you have seen so far by me, in the sense that in all those lectures we were trying to design FPT algorithms. In this lecture we'll be trying to say that, okay, why for some problems we don't believe that we can design FPT algorithms. Okay, so it's like the reverse of what we had been doing so far. So today's lecture is about hardness or lower bounds in the FPT world. Okay, but even before talking about hardness, let's talk about some algorithms. So we all had seen a vertex cover algorithm almost every day. I think probably except yesterday, we almost every day saw a vertex cover algorithm. We saw a kernel for vertex cover. We saw a branching algorithm for vertex cover. Iterative compression also through vertex cover, right? So what sort of an vertex cover? We saw a k-square kernel for vertex cover. We also saw a 2k vertex kernel for vertex cover using LP. We saw a 2-par k branching algorithm for vertex cover, 1.618 par branching algorithm for vertex cover, 1.4656 par k branching algorithm, then again a 2-par k algorithm using iterative compression. So we saw a lot of algorithms for vertex cover. Okay. But what we didn't see all this while, or what we didn't talk about it all this while, is an algorithm for independent set. Right? But why do you think we didn't talk about independent set? Okay, so because it's n minus vertex cover, and so give me an algorithm for independent set, and we are designing FPT algorithms, right? Okay, so again we are solving the decision version of the independent set problem, and we are given a graph G as input and an integer k, and the task is to find if there is an independent set of size at least k in the graph. So what is the algorithm that you propose? Okay, how much time will that take? So if we have to solve, so the reduction that you have seen from a vertex cover to independent set, what does it do? So let's say vertex cover, and suppose you are reducing it to the independent set problem. You are given an instance g comma k of vertex cover. You say, you create an instance g comma n minus k of independent set, right? So a graph has a vertex cover of size k if and only if a graph has a independent set of size at least n minus k, right? So now I have asked you, can you find an independent set of size at least k in the graph? For that, as he says, it's enough to compute a vertex cover of size at most n minus k in the graph. Okay, so you will use any of these algorithms. Say, let's use the simplest algorithm. We use this algorithm for vertex cover. But what is k for this vertex cover problem? We are looking at a vertex cover of size. So how much time will this algorithm take? 2 power n minus k into some polynomial factors, right? Is this an FPT algorithm for independent set? So this also tells us one thing. So normally when I've seen a lot of people, in fact when I was young or doing my undergrads, even we used to say things like this. Okay, if you can solve, like if suppose I was able to give a polynomial time reduction from vertex cover to independent set, my reaction would be, you know what, if you can solve independent set, then you can solve vertex cover. So this is like the language which we use, but this language is too vague, and it's most of the times wrong. Of course, if you can solve independent set, then you can solve vertex cover, but the times are important. If you can solve independent set in polynomial time, and if it's a polynomial time reduction, then you can solve vertex cover in polynomial time, right? So then that doesn't mean that if I give you the same reduction, and if I say that, okay, if you can solve independent set in FPT time, and I give you a polynomial time reduction, then you can solve vertex cover in FPT time, right? So when you're giving reductions, so all these reductions, when we design reductions for problems, we want to say that, okay, if certain kind of problems can be solved in certain kind of time, then certain other kinds of problem can be solved in certain other kinds of time. And all these kind of times depends on precisely what the reduction is, like what the details of the reduction are. This might be a polynomial time reduction, but we also have to look into, like for example in this case, how does the parameter change when we perform the reduction. Here the parameter goes from k to n, right? So when we are designing reductions, you have to be very careful. So this would immediately tell you that, okay, if we had to show some hardness for FPT algorithms, or in other words, if we had to prove that certain problems are FPT, and suppose, like for example, we know 3-SAT, like how many of you have seen the proof that 3-SAT cannot be, like it's unlikely that 3-SAT can be solved in polynomial time? Just raise your hands, whoever has seen the proof. To prove NP hardness of problems, you start with 3-SAT. You know 3-SAT is NP hard, and you prove that certain other problem is NP hard, and then because these reductions are transitive, so suppose you have proved that you have given a polynomial time reduction from 3-SAT to vertex cover, then you know vertex cover is also NP hard. And then to prove NP hardness of any other problem, now you can either start from vertex cover or 3-SAT. So they are equivalent in that sense, but to prove that 3-SAT is NP hard, where do you start from? Okay, and then I'll tell you, okay, so give me a proof for, to prove that general SAT is NP hard. So most of you don't know the proof of it, and that's okay. Even I learned about the proof of it only during my masters. It's not very complicated. So what the proof goes like this. So if you have any problem in NP, so I don't know how many of you know about Turing machines, but again, for those of you know, as I said, I'll be using a lot of jargons today. So if you have a problem in NP, then there is a non-deterministic Turing machine for that. So how the proof goes about at a very broad level is, it looks at this Turing machine, it looks at the computation steps that Turing machine would go through when it is given some input, and it tries to encode those computation steps in some way into the CNF SAT problem, and this is how it goes at a meta level. So basically, see, for proving NP hardness, you have to say that any problem in NP can be reduced to 3-SAT. Any problem. So you can't pick one problem, prove that it reduces to 3-SAT, and so on. So to prove that any problem in NP can be reduced to 3-SAT, you look at the general framework that any NP problem would exhibit and try to encode that general framework into the 3-SAT. So this is how it goes like. So again, why I ask you is because again, for the FPT world also, someone had to so the way it goes is, someone proved the first problem. So someone gave a problem and proved that it is unlikely to exhibit an FPT algorithm. It's unlikely to exhibit an f of k into polynomial time algorithm. So someone did that, and henceforth all that we have been doing is we have been trying to give appropriate reductions to starting from that problem, giving an appropriate reduction that would imply that if I start with the problem A, which someone has proved that it cannot have an FPT algorithm, okay, and then all we try to do is we try to give an appropriate reduction that reduces A to B, and we say that, and the kind of reduction, it should be a kind of reduction that allows us to say that, okay, if this is the kind of reduction that you give, and if you give me an FPT algorithm for this problem, then I can definitely give you an FPT algorithm for A. For example, for a very simple example, of course, this will not make sense. Suppose, for example, in some way, I was able to reduce vertex cover to independent set in such a way that if you give me an instance of vertex cover, GK, I was able to construct another instance of vertex cover, an instance of independent set, G prime, comma, let's say as of now, K. Okay, suppose G prime was some graph I could construct it in some way, and I was able to say that if G has an independent set of size at most K, if G had a vertex cover of size at most K, then G prime has a vertex cover independent set of size K, and if G prime has an independent set of size K, then G has an independent set of size K. Suppose I was able to give such a reduction. Now we can prove this FPT thing, right? Now suppose independent set was FPT. If it had an f of k into poly and algorithm, and suppose as of now this reduction was taking polynomial time, then can you give me a polynomial? Then can you give me an FPT algorithm for vertex cover? Because to give an algorithm for vertex cover, what will you do? In polynomial time, you'll reduce it to this instance of independent set, and you'll solve this instance of independent set in this much time. So the total time taken to solve this instance of vertex cover will be this polynomial plus this much time. So this is if I give this kind of a reduction. Now observe what is this kind of a reduction. At least one simple property that I've tried to ensure here is that k goes to k. Like this k here goes to k. Like the parameter remains a function of k, for example. So that when I give, if I have an FPT algorithm for this problem, I look at that FPT algorithm, it will be some f of k, and if a function of this k, then this function will be a function of this k alone, right? So, okay, or let us just let us say this was k prime. So given an instance g comma k of vertex cover, I was able to convert it to an instance of g prime k prime of independent set. Then and then if suppose I had an FPT algorithm for independent set, FPT algorithm for independent set problem, then it would run in f of k prime into polynomial in n time. And if this k prime was some function of the original parameter, like some function of this k, then I can solve vertex cover in the following way. In polynomial time, I'll create this instance, and then I'll solve this instance in this much time. So the total time taken would be some polynomial plus f of k prime into poly n. Now f of k prime is nothing but some f of g of k, and this is nothing but some h of k. So this is some FPT algorithm for vertex cover, because this is some h of k into polynomial in n time algorithm, right? So of course this is a very stupid example, because for this problem you can't get such a reduction. But my point is, if suppose you were able to get a reduction where this, like the parameters that we have in the reduced instance are a function of the parameter of the original problem, then there is a scope that if I give such a reduction, then I can conclude similar things. So when I say similar things, as in if this had an FPT algorithm, then this has to have an FPT algorithm, right? Or in other words, if this problem, the problem from where I am starting with, does not have an FPT algorithm, and if I give you such a reduction, then this problem cannot have an FPT algorithm. So these are the kind of things that you prove during NP hardness also, right? It's like the game there is about polynomial time algorithms. There you say, okay, if you give me such a reduction, and if you know that this has no polynomial time algorithm, then you can't give me a polynomial time algorithm for this, because if you gave me a polynomial time algorithm, I'll reduce the instance of this problem to the instance of this problem in polynomial time, and I'll solve this instance and I'll solve this problem in polynomial time by using the black box algorithm, polynomial time algorithm for B, right? So this was the idea. So let me just try to make some things concrete here. For in the FPT world, the first problem to be proved the first problem which people proved that should not exhibit an FPT algorithm was the clique problem. Okay, so what is this clique problem? You're given as input, you're given a graph G and an integer k, and the question is, you output yes if G has a k clique. K clique meaning it has a set of k vertices which form a complete graph. There is an edge between both the endpoints of it, and it says no otherwise. So clique is like the 3-sat in the FPT world. So it is believed that there is no polynomial time algorithm for 3-sat or sat. It is believed that there is no f of k into polynomial in n algorithm for clique. So this is like the standard thing that we assume and we start. So if I have to prove that a problem is not FPT, I start from the clique problem and give an appropriate reduction. So we'll formulate what this appropriate reduction is to that problem, and that appropriate reduction would help us conclude that, okay, if that problem had an FPT algorithm, f of k into polynomial time algorithm, then clique would have an FPT algorithm. And because we believe that clique cannot have an FPT algorithm, then this problem should not have an FPT algorithm. This is how the reductions which prove that problems do not have FPT algorithm go about. Okay, just some idea. Again, it's a very intuitive idea as to why people believe this clique problem should not have such an algorithm. Okay, just some idea. So why do people believe that? Do you know? Have you done a TOC course? Any one of you? Some people, you've done it. Who else? Theory of computation, automata, or Turing machines. Has anyone done it? If you've done it, just raise your hands, because I'll not ask technical questions, so that I just know that if I'm saying something, it makes some sense. It will not make complete sense anyways, but just raise your hands. Whoever has done a TOC course, good, bad, ugly, I don't care. Who understood, not understood, I don't care. You've done it? Yeah, so some of you, okay. So, okay, I'm sorry about some of you, but at least for those of you who have done it, let me just try to say something. so that they get some idea, because they've seen Turing machines. For those of you who have not done it, it's okay, because you've anyway seen, and when you did NP hard reductions, you anyway assume 3SAT is NP hard and you started doing that, right? So here also you can assume that click cannot have such an algorithm and start doing it. And those of you who have done Turing machines, see for you, why do people believe that 3SAT, like one very simple reason why people believe 3SAT does not have an polynomial time algorithm. Why is it? Or in general, why do people believe that it should not be the case that all problems in NP should be solvable in polynomial time? So, okay. So, see just try to understand what I'm trying to say. Let's see if it makes sense. So, what is an NP problem? An NP problem is a problem for which there is a non-deterministic Turing machine that runs in polynomial time. So what is a non-deterministic Turing machine? At every point of computation, it makes a guess into, say, without loss of generality, 2 branches and does something. So it runs in some polynomial steps. So like at every step, it makes 2 choices. So note that if you have, if there is a non-deterministic Turing machine for a problem, then you can always solve that problem in exponential time, because instead of guessing, you do you perform both the computations and check, right? So why people believe that all NP problems should not be solvable in polynomial time is because it's okay, in fact, let's look at a layman example and we'll come to it again. Suppose I give you 2 tasks. To one set of, okay, I divide the class into 2 parts and I say that to both the parts I'll be giving a problem, and I am claiming that, okay, whatever problem I've given to, there'll be different problems, okay, so that there are different problems and it's a competition between both of you to solve the problem. And my claim is that, see, I've been fair, I've given the problems that I've given to both the classes have the same level of difficulty, so that, because if I give different problems, there is always a question of, maybe I'd given that group an easier question and I've given the other group a hard question, right? There is always such a question. But what I'm claiming is, no, I'm being fair, and the problem that I've given to both the groups has sort of same hardness. Of course, they're different problems. I'm claiming that, and now let me tell you what problem I'll give you, and now you have to tell me if I'm really being fair or not, okay? To one problem, to one group, for example, what problem you have not seen? Say yes. So for one group, I give you a graph G, okay? I say draw a graph, but it's a huge graph. Like I draw the graph on this board with like tiny vertices, okay? So like it's a huge graph I've given you, but it's huge. But anyway, what I've told you is I've also given you a set of vertices. So to say this group, I've given you the graph and I've given you a set of vertices, some let's say 2 or 3 vertices, and I've told you, can you check if after I delete these vertices from the graph, this graph has no cycle, okay? So I've given you a set of vertices and I've told you this, and to the other group, I've given you the question, I've given you the same graph and I don't give you the set of vertices. I tell you, find a set of 5 vertices whose deletion will kill all cycles in the graph. What do you think? To which group have I been lenient? To which group have I given the easier answer, easier question? Yeah, so at least it looks like I've been unfair, right? I've given easier things to you. And that's exactly, so all of you, like everyone in this class believes that, does everyone in this class believe that I've given an easier problem to them? Is there anyone who believes no, it's more difficult to them, or they're equal? So if everyone believes that I've given an easier problem to them, then all of you should believe that P is not equal to NP. You can't believe, then you can't believe that P is equal to NP. It's because P equal to NP is almost the same problem. P are the problems for which I'm asking you, I've given you a problem and I'm asking you, give me an algorithm that finds a solution. And NP is like, so again, for those of you who have done Turing machines, it's like I give you a certificate, I give you a set of problems, and all I ask you, just check if this is the solution, right? So they don't look like both these problems should have the same difficulty level, right? So this is why people believe that P is not equal to NP, and hence people, the question I started was why people believe 3SAT can't be solved in polynomial time, because they already had a reduction from all NP problems to 3 SAT. So if 3 SAT was polynomial, 3 SAT was could be solved in polynomial time, then all NP problems could be solved easily in polynomial time, and that's something that people don't believe, right? And yeah, coming to Turing machines, so Turing machines is like, so a non-deterministic NP is all the problems for which you have a non-deterministic Turing machine. So at every step the Turing machine makes 2 guesses, okay? So in that sense, if you look at the computational, if you look at the kind of decisions that a Turing machine makes at every step, you can simulate it using a deterministic Turing machine that would run in 2-power polynomial in n time, because instead of guessing, you go to both the branches, right? So similarly, for this click problem, there is something called a short acceptance Turing machine, okay. I'm not sure if I'll tell you what that is, but something called short acceptance Turing machine. And what people said was, all the problems which can be solved using this short acceptance Turing machine, look at this set of problems, and they gave a reduction from this set of problems to click. The way people give a reduction from all the problems in NP to 3 SAT, for this they give this reduction from this short acceptance Turing machine to click, okay. And now why people believe that after giving this reduction one cannot have such an algorithm? It's because if you look at this computational tree of this short acceptance Turing machine, it's like a non-deterministic Turing machine, which say goes only till k steps, something like that, okay. And if you look at this computational tree of this short acceptance Turing machine, it will have some n choose k paths in it. The way a non-deterministic Turing machine can have 2-power n paths depending on which branch it takes, a short acceptance Turing machine has something like n choose k branch paths, okay. So again, once you give a reduction from short acceptance Turing machines to click, the question is, how likely is it that all the problems which have an algorithm that runs in time n choose k will have an algorithm of this running time? Like we said, NP is all the problems for which there is an algorithm that runs in 2-power n time, right? And the question is, for all those problems, how likely is it that all those problems will actually have polynomial time algorithms? So there we were trying to compare 2-power n with poly in n. Here the question is, how likely is it that if a problem has an algorithm that runs in n choose k time, so n choose k is like roughly n power k. So how likely is it that if look at any problem that has an n choose k algorithm, then it must have this kind of an algorithm? Again, of course, it's slightly different, but again, look at these two numbers. I mean, there is no reason to believe that every problem which will have an n choose k algorithm will have an f of k into polynomial int n algorithm, right? So again, as I see, there are less number of people who are convinced that this is making sense. Like, how likely is it that if a problem has an n choose k algorithm will have an f of k into polynomial in algorithm? And again, this is exactly the status outside this class. A lot of people believe that this should be the case. It should not be the case that look at any problem that has an n choose k algorithm should have this kind of an algorithm. But again, the people who believe this statement are, let me say, a strict subset of people who believe that P is not equal to NP. So it's okay. If you're not very convinced, it's okay. There are, like, this is the status in general world, okay. But still, a lot of people believe that this should not happen, and hence they've just developed a theory. Assuming that this does not happen, they've developed a theory of hardness for FPT algorithms. So basically, assuming that click cannot be solved in this much time, they just try to give some reductions, okay. So like this is like the sort of intuition or whatever, some broader level reasoning about why we believe click to not have such an algorithm, and why we have set up the theory of hardness for FPT problems around click. Like they have set up a theory of NP hardness around 3 SAT. Okay. So henceforth, assume click has no f of k into polynomial in an algorithm, and from there we want to conclude about certain problems that they don't have f of k into polynomial in algorithms. Okay. Now let me come to this concept of what are parameterized reductions. Okay. So what are parameterized reductions? You have a problem A and you have a problem B, and you give a reduction from problem A to problem B. This is like you give a reduction, you give an NP hardness reduction from problem A to problem B. You have an instance of problem A, you have an instance of problem B, and you want to reduce the instance of problem A to an instance of problem B, such that both these instances are equivalent. So if this is a yes instance of problem A, if and only if this is a yes instance of problem B. Okay. And just for the sake of simplicity, let's just assume we are working with graph problems and their decision problems. So like an instance of A will look like, let's say, G comma K. Instance of B looks like G comma K. Okay. And like I've just taken this example in a more general case, as we had seen in the first class. When we talk about parameterized algorithms, it's like you can have a, like you could have chosen vertex covered. All the examples that we saw for vertex covered, we had the parameter as k. So we are designing algorithms which were of the form f of k into polynomial ln. But as I said in the very first class, for any problem there are multiple choices of parameter. You could parameterize, like we also saw vertex cover parameterized by OCT in the first class. We could have parameterized by FVS of the graph. There are a lot of parameters. So basically, in general, we will not have k here. We'll have a parameter, whatever. Let's say. So this will be an instance of the problem. Like for vertex cover, it will be, let's say, G comma k, and or dominating set G comma k, and this is like the parameter of the problem. Anyways, if we don't get it, fine. Like let's assume we are we are only looking at problems parameterized by the solution size. So if it's vertex covered, we are looking for a vertex cover size at most k and an algorithm of the form f of k into polynomial n and something like that. Okay. So what is a parameterized reduction? Let's see what I want from the reduction. I want to say the following. Suppose I know that A has no f of k into polynomial in n algorithm. From there, I want to conclude that B has no f of k into polynomial in an algorithm. Right? This is what I want to do. Now, what should be the property of this reduction? First of all, how much time should this reduction take? So again, like think about this is nothing but this is similar to the NP hardness reduction, but we have to be more careful. As we saw, this vertex cover to independent set reduction won't work in this setting. So when I say how much time this reduction has to take, what should it depend on? We are trying to say that A has no f of k into poly n algorithm, and we assume that B has an f of k into polynomial time algorithm. So from there we want to say that, okay, if B had an f of k polynomial time algorithm, then A should have. This is what we want to say. So can this reduction take, say, 2 per n time? Suppose I give you a reduction which takes an instance of problem A and takes, let's say, 2 per n time and gives us a reduction instance of problem B. Okay. And the statement that I want to make is the following, that if B has an f of k into polynomial time algorithm, then A has one. I want to say this statement. Now, if this reduction was taking 2 per n time, will I be able to say that? No. Why? Yeah. So when we give this reduction, what are we giving? Basically, we are giving an algorithm for problem A, which will be as follows. Given an instance of A, we'll do this reduction, reduce it to an instance of B, and then solve and then use the algorithm for problem B. So the total running time for problem A will be this, the time taken by this reduction and the time taken by the algorithm of B, right? So then all this says is that if B has such an algorithm, then A will have an algorithm of the form 2 per n plus this, okay? And then we don't get any contradiction. So when we are proving hardness, we want to get a contradiction to the fact that A has no f of k algorithm. So this is not giving a contradiction. Like this is not an f of k into polynomial time algorithm for A, right? So what kind of running time should this reduction take? Poly n, right? So if you want to claim these sort of things, this reduction should take some f of k into poly n time, right? So fine. So basically we are looking at reductions that can take f of k into polynomial in n time. Note that if it's a polynomial time reduction, then also, I mean, any polynomial time is an f of k into polynomial in n time, right? F of k being a constant function, right? It's just that when we are designing parameterized reduction, we also have this leverage that our reduction could take f of k times. So we have got much more power than we had for NP hardness, okay? But yeah, with power comes responsibility, in the sense that, okay, we have this power, but there is something that we didn't care about in NP hardness proofs, but in this case we have to care about, and that is, how does the parameter change? As we saw for the case of vertex cover, if I give a reduction, so basically what will this reduction be? It will take an instance of g comma k of A, and it will give an instance g prime k prime of B, and over this instance I'll run this algorithm, right? And as we saw, if this k prime was a function of n, then this running time will be some function of n, okay? And when I say, okay, let me just write n prime here. So n prime is the number of vertices in G prime, say, and n is the number of vertices in G. Eventually we want to design an algorithm for A that has running time f of k into poly n, and we'll use an algorithm for B. So look at G prime, the number of vertices in G prime is n prime. When I use an algorithm for B, it will run in this much time, f of k prime into n prime, polynomial in n prime. So clearly the reduction should not be such that the size of G prime becomes, let's say, 2 power n or any weird thing. The size of G prime should remain polynomial in the size of G. Is that all that we can say about the size of G prime? Like, do we strictly want that when we do our reduction, let's say size of G prime is n prime, do we strictly want that in our reduction the size of n prime should be some polynomial function in n? Or can we again take some leverage here? So for example, again, if I give you a polynomial time reduction, this would have been good enough for us to prove our claims, but we saw that, okay, I can even allow more time to it in this reduction and still prove the kind of claims that I want to, right? Similarly, of course, if you give me a G prime whose size is polynomial in n, this could go through. Of course, modulo k prime is also well behaved, but the point is, even if the graph G prime that you construct has size some, let's say, g of k into polynomial in n, then also it's not a problem, right? Because when I'll use this algorithm for B, n prime would be g of k into polynomial in n. So the total running time will be f of k prime into g of k into polynomial in n, right? So this is still good enough for me, provided f of k prime is some h of k, like it's some function of k, because in that case I'll have some h of k into polynomial in n time algorithm for solving B, some f of k algorithm for this reduction, and hence I'll have some FPT algorithm for A, right? So again, in this reduction we can also allow this G prime, the reduced instance, to have whose size is some FPT function, like some g of k into polynomial in n. Even if I give a reduction where the size of g goes like this, I'm good enough. Okay. Again, this kind of a thing we didn't have in NP hardness proofs. In NP hardness proof, the reduced instance should be a polynomial function of the input instance, right? Okay, so this is one, again, this is one leverage that we can allow. So these are the two leverages we can allow. But here comes the constraint, so about k prime. So in an NP hardness reduction, we didn't care about k prime. K prime could be anything. For example, remember you would have done a reduction from 3-sat to vertex cover in the very first class, right? So do you remember what was it? So we were given a 3-sat instance, we reduced it to vertex cover. Like this was, yes, if and only if this had a vertex cover of size something. What was that something? Roughly, like what was it? It was a function of the number of clauses in 3 set, right? So it was not a, like, it depended on the input size of 3 sat, the number of clauses there. And we were okay with it because anyway, we were talking about polynomial time algorithms. We would run vertex cover in polynomial time and that would give us this. But here, the running time is a function of k prime. If I have k prime, which is, let's say, a function of the number of vertices in the graph, or if I was starting with a 3 set formula, the number of clauses in the graph, then again I can't prove such a thing because this f of k prime will then become a function of n or m, right? And then I can't get such a thing. So if I want this reduction to hold, k prime should be a function of k. Okay, I'm writing f here again, like this f and this f are not same. When I'm just falling out of variables. So when I say f of k, it's just some function of k. This f of k is some function of k. They might not be the same functions of k, like just some functions of k, okay? So when I do this reduction, I necessarily want my k prime to be some function of k so that this reduction can go through. So there are 3 things. I'll write them down clearly in the next slide again. What we discussed is, if I want to show some negative results for hardness using reductions, and if I start with a problem for which I know has no f of k into polynomial time algorithm, then if I give the following kind of reduction, which is the reduction takes some f of k into polynomial in n time, and at the end of it, it returns an instance of another problem where the instance has size some g of k into polynomial in n, and the parameter has size some f of k, then it cannot be the case that then we have the following. Then if B is FPT, if B has an algorithm of the form f of k prime into polynomial in the size of g prime, then A will indeed have an algorithm of the form f of k into polynomial in n. So to begin with, if A didn't have such an algorithm, then B also shouldn't have such an algorithm.